Hello everyone, I'm Samadhi, a graduate student in Dr. Dongmao Zhang's group. This video gives an overview of how solvent Raman intensities can be used for the quantification of effective excitation and emission path lengths to correct the sample inner filter effect in spectrofluorometric measurements. Fluorescence spectroscopy is a technique that is concerned with the vibrational and electronic states of molecules. The species in its ground state is first excited by absorbing photons to one of the vibrational levels in the excited electronic state. A typical spectrofluorometer is set up for detection of photons at a 90-degree angle. This instrument setup allows for the detection of both fluorescence and scattering within limits of detection approximately 3 orders of magnitude lower than absorbance spectroscopy. Therefore, spectrofluorometers can be used to detect fluorescent spectra, light scattering spectra, and even circular dichroism. Fluorescence is mainly used in biochemical, medicinal, and chemical research fields. It is a popular technique because it not only requires the use of small sampling volumes, but it gives high selectivity and sensitivity. A common problem in fluorescence spectroscopy is, however, the inner filter effect. The inner filter effect is caused by absorbers and scatterers in the medium that can attenuate the fluorescence intensity. The inner filter effect can lead to a decrease in either the number of excitation photons reaching the fluorophore or emission photons that reach the detector. This can lead to spectral distortion and nonlinearity between the spectral signal intensity and analyte concentration as the concentration of the analyte is increased. Let's look at the following figures. Figures A and C show the UV-vis absorption and fluorescence spectra of the fluorophore aminopurine. It is evident that the UV-vis absorption is linearly related to the concentration of the aminopurine. However, the corresponding fluorescence emission deviates from linearity at higher concentrations of the aminopurine. This deviation is due to the inner filter effect. It has been shown that the inner filter effect is related to the sample UV-vis intensity at the excitation and emission wavelengths and the effective excitation and emission path lengths of the spectrofluorometer. There are numerous methods in literature to correct the inner filter effect. Equation 1 and 2 are two methods that have been frequently used. In these equations, I observed and I corrected are the fluorescence intensities before and after the inner filter effect correction. A lambda x and A lambda m are the UV-vis intensities of the sample at the excitation and emission wavelengths. The cuvette used has dimensions of 1 cm square and the effective excitation and emission path lengths are assumed to be 0.5 cm. As can be seen in the diagram, the excitation photon will travel 0.5 cm into the cuvette and the emission photon will travel 0.5 cm before exiting the cuvette. This assumption, however, is problematic due to the imperfections in the optics and optical alignment. The correction parameters of D, S, and G in equation 2 are the cuvette length, photon excitation beam width, and the nominal emission beam path length. Even though these methods have been applied extensively in literature and are conceptually simple, independent and robust evaluation of the integrity of these methods are really challenging. This is because of several reasons. The occurrence of competitive photochemical and physicochemical processes that can change fluorophore fluorescence, unsatisfactory results when applied for independent sample validation, and the impact of various instrument parameters such as the optical alignment all make these two equations erroneous. So to overcome these challenges, our group developed a new method to correct the fluorescence and Raman inner filter effect by using water Raman intensities. This work was published in the Analytical Chemistry Journal in 2015. And if you are interested in learning more, you can access this paper online. The novelty of this work is in the characterization of the Raman inner filter effect and using the Raman inner filter effect to determine the effective path lengths of the spectrofluorometer. First, let's get to know what the solvent Raman peak is. It arises in the emission spectra due to the inelastic scattering of the incoming light. This is known as Raman scattering. As seen in the equation, the shift in the wavelength and the Raman peak is always a constant. As a result, the peak resulting from the Raman scattering when change in the excitation wavelength can be used to identify the Raman peak in the fluorescence spectrum. Why use Raman intensities? Firstly, the Raman measurements are robust. Also, the degree of Raman inner filter effect in a chromophore-containing sample can be reliably quantified by simply dividing the control signal generated from the sample that does not have the chromophore by that of the chromophore-containing sample. This contrasts with the fluorescence measurement, where it is impossible to conduct inner filter effect measurements even for control samples. Given are the UV-vis absorption and water Raman spectra for a solution containing a mixture of chromophores. The water Raman spectra in figure B is taken at an excitation wavelength of 300 nanometers, as this is the wavelength at which maximum absorption is observed. Figure C is the water Raman spectra for the same sample when excited at 480 nanometers. The arrows show the direction of spectral change with increasing chromophore concentration. At 300 nanometers, the absorbance increases as a function of chromophore concentration, while the water Raman signal intensity at 300 nanometers decreases as a function of chromophore concentration. The water concentration only changes by less than 2%, so it cannot cause a drastic change in the signal intensity. As you can see, at 480 nanometers, the absorbance is concentration independent, since the chromophore does not absorb light at this wavelength. We can see that the water Raman intensity at a wavelength of 575 nanometers is also concentration independent. The drastic difference in water Raman intensity suggests that the inner filter effect is causing a reduction in the Raman intensity. The method developed by our group is a performance-based method to determine the effective excitation and emission path lengths for fluorescence and Raman inner filter effect correction. This method considers water Raman intensities obtained at different chromophore concentrations. I corrected and I observed are the Raman intensities of the water control and the chromophore containing samples. A lambda x and A lambda m is the UV-vis intensity at the excitation and Raman photon wavelengths. dx and dm are the effective excitation and emission path lengths, which can be determined by optimizing the Raman inner filter effect. Fi is the water Raman correction factor obtained by dividing I corrected by I observed. With a simple mathematical rearrangement, equation 3 can be converted into equation 4. With this, the effective excitation and emission path lengths can be obtained from the intercept and slope through a linear fitting. Let's look at the procedure for water Raman standard preparation. Here we have used two chromophores, nickel sulfate and potassium dichromate. The reason for using two chromophores is discussed in detail in the publication. The final concentration of nickel sulfate should be constant in all the standards. The potassium dichromate is changed from 1 to 0.5 millimolar. After preparing the solutions, we can take the UV vis and Raman spectra for these solutions. Also, we need to run a water control using the same cuvette. The cuvette used had a path length of 1 cm and a slit width of 5 nanometers. Let's move on to the data. Figure A for the chromophore mixture shows that UV vis intensity has increased with increasing chromophore concentration. The corresponding Raman spectra was acquired at an excitation wavelength of 350 nanometers. Even though the UV absorbance is seen to increase with the concentration of chromophore, the Raman signal intensity does not increase with increasing concentration. The arrow indicates the direction of spectral change. When the Raman excitation and emission are in the region where the chromophore shows maximum absorption, water Raman signal intensity of the chromophore mixture decreases with the increasing chromophore concentration. This is due to the inner filter effect. As can be seen, the effective excitation and emission path length was determined successfully through linear curve fitting of water Raman data collected in B. According to equation 4, the slope and the intercept are 0.56 and 0.59 respectively. This indicates that the effective excitation and emission path lengths for the spectrofluorometer are 0.56 and 0.59 nanometers when a cuvette of 1 cm square and a slit width of 5 nanometers is used. As can be seen, the effective inner filter effect corrected water Raman intensity is independent of the chromophore concentration. Independent validation of these effective path lengths for correcting Raman signal is shown using the following chromophores. As can be seen, this validation is done using concentrations different to the ones used in the previous slide. Figures A, D and G show the concentration-dependent UV vis spectra of these chromophores, and B, E and H shows the corresponding Raman spectra. Again, the arrows point in the direction of increasing chromophore concentration. After the correction, figures C, F and I show that the water Raman intensities are independent of the chromophore concentrations used. It is important to note that the excitation and water Raman photon wavelengths among these three compounds are very different. It is even different from the samples used to calculate the path length. Next, let's look at how the effective path lengths obtained with water Raman measurements are directly applied for real-life fluorescence inner filter effect correction. The fluorescence spectra are acquired with the same spectrofluorometer under the same instrumental configuration. Here, we have used two model fluorophores, Kumasi Brilliant Blue R and aminopurine. Figure A and E shows the UV vis absorption spectra. B and F are the as-acquired fluorescence spectra, and C and G are the inner filter effect corrected fluorescence spectra. D and H shows the correlation between peak fluorophore intensity as a function of the fluorophore concentration. In D and H, the black dot shows the trend line at 300 nanometers for the as-acquired intensity. The red, green and blue dots symbolize the intensities obtained after correcting the inner filter effect using equation 1, 2 and 3. As can be seen, the peak fluorescence intensity for the as-acquired fluorescence spectra have a poor linear correlation to the fluorescence concentration. Even equation 1 and 2 doesn't give a satisfactory linear correlation. But there is excellent linear correlation observed when equation 3 is used, suggesting a superior inner filter effect correction. Please note that in this case too, the excitation and emission wavelengths are different, providing further evidence that the effective path lengths are instrument-specific but sample-independent. Also, the same pair of path lengths can be used to correct both Raman and fluorescence inner filter effects. These data show the critical importance of the reliable determination of effective path lengths for inner filter effect correction. Our method of water Raman intensity-based path length determination has several advantages. It's highly reproducible and robust. The effective excitation and emission path lengths should be redetermined only when a new instrument configuration is used. Also, the same set of water Raman chromophore mixtures can be used each time. We have extended this work to one of our recent publications titled Back to the Drawing Board, a unifying first principle model for correlating sample UV vis absorption and fluorescence emission, which is available online. This technique will be discussed in detail in a later video. Thank you for your attention.